AC generator is an electric generator that converts mechanical energy to electrical energy in the form of an alternating EMF or alternating current. Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip rings and a load, which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation. Graphical representation of induced EMF. Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, the armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily 0. Hence, the induced EMF at this position is 0. During the first quarter rotation, the induced EMF increases. Then, at time t upon 4 seconds, the armature becomes horizontal. At this position, the rate of change of magnetic flux momentarily attains the maximum value. Therefore, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then, at time t upon 2, the armature again becomes vertical and therefore the induced EMF is 0. During the third quarter rotation, the induced EMF increases but has an opposite polarity as compared to that of the first half rotation. At time 3t upon 4 seconds, the induced EMF attains its maximum negative value. During the fourth quarter rotation, the induced EMF decreases and becomes zero momentarily at time t seconds, as the armature is vertical once again. So the magnitude of the induced EMF is sinusoidal.